Hello everybody, welcome to lesson 16.1.2, dealing with isotopes and decay sequences. First thing we're going to do is we're going to take a look at what we call isotope notation, which is really just a way of writing a different isotope. Remember, an isotope essentially is a variation of a particular atom. And so we got a couple of examples here. Here we've got 3 isotopes of nitrogen. The main difference here is the number of neutrons found within each one. Same number of electrons in all 3 cases, 7. Same number of protons in each case, 7. But here we've got 7, 8, or 9 neutrons. Now, 7, 8, 9. So as we take a look here, in each case we would use the symbol N to represent the atom. Rewrite that one there. Okay, the little z here we're going to use as the charge on the nucleus, which for the most part deals with the number of protons found in a nucleus of an atom, although there's a specific reason why we're doing that. And so all of these have a charge of 7 in the nucleus. And the top number here, the A, is the mass number. So given that we've got 7 protons and neutrons in this first, that would be a mass of 14. This would have a mass of 15, and this would have a mass of 16. And so that is the isotope notation. These numbers are essentially based on what we call the atomic mass unit, which is defined exactly as the mass of, based on the mass of a carbon-14 atom. So we take the mass of carbon-12 and divide it by 12, and we get exactly this number. The reason why carbon-12, which if you were to add the protons and neutrons, and you wind up with a mass that's a little bit heavier, being that you've got masses of protons and neutrons to 3 significant digits, being 1.67 times 10 to the negative 27 kilograms. The reason for that mass difference deals a lot with the energy holding that nucleus together, and we'll be taking a look at that difference in mass at a later time. So let's take a look at a few of these examples here. Protons and neutrons found within each of these atoms. First of all, we got an iridium-169. Now, on your periodic table, you will notice that iridium has a mass of 192. And this seems quite a distance off. Iridium has a huge number of isotopes. Last I looked, I think it was somewhere in the neighborhood of 33 or 34 different isotopes. It could even be more now. And so 169 is one of them, where the number of protons will be the charge of the nucleus, so that's 77, that's relatively straightforward. And the number of neutrons, well, if we've got 169 atomic mass units, 77 of which are protons, that makes 92 of them neutrons. And we're basically getting that by taking 169 minus the 77. Here we've got tin-103, 50 protons, 53 neutrons, and again this 53 comes from taking the 103 divided by the 50. And Einsteinium-99 has 99 protons and 151 neutrons. Taking a look and identifying the elements that have this particular isotope, mostly we're going to focus in on that charge of the nucleus, that nucleus charge. in order for us to find out which atom it is, because that will match the atomic number. So number 63 in the periodic table is EU, or europium. Number 19 on the periodic table is K, which is potassium. And number 94 on the periodic table is U, or uranium. Now, we use this isotope notation mostly to deal with the decay sequences. And there are three major forms of nuclear radiation, and known as alpha, beta, and gamma. And this happens when atoms that are radioactive will release these particles and will wind up breaking down slowly into other more stable ones. For example, uranium-235 can wind up becoming lead-206 through a series of decay sequences. Okay. Now, the initial classification was based on how much each type of radiation could penetrate. Alpha could penetrate the most, beta second, and gamma the least. But as we take a look at this particular sheet, where we're trying to say, okay, what do we know about the electrical properties? The magnetic field here is coming out of the page. And so we use our pointer fingers for that. The initial velocity in all three cases is this direction, and so we use our thumb for that. And we see the gamma radiation does not deflect, so it has no charge. The alpha particles bend this way, which corresponds with the thumb on the right hand, and thus indicating a positive charge. The beta will be the thumb on the left hand, and thus indicating a negative charge, using either right or left hand rule. Now, in this case, right, because that would be the way that each of these are forced. So it's difficult for me to show, but your thumb is always pointing to the right. Your pointer finger is always pointing out of the page or towards you, and we see that the left hand has the thumb pointing up and the right hand pointing down. And so that's the nature of the three charges. The alpha particle deflects a lot less than the beta particle because the alpha particle has more mass. So with the force, here we're going to see a much larger radius of curvature. Now, there are two things that are always conserved with radioactive decay. The first one is the charge, which means those Z numbers at the bottom. These numbers here are always going to be conserved. What we have at the beginning is the same as what we have at the end. The other one is the atomic mass numbers. These are also conserved. Okay, and that just means that the law of conservation of mass, the mass you have before equals the mass you have afterwards. Now, since all these decay sequences have been discovered, have vastly more mass than an electron, there's practically no recoil on the daughter nucleus during a beta decay. Beta decay basically meaning electron decay. Consequently, Physicists expected virtually all of the energy released in beta decay would appear as kinetic energy emitted. However, measurements found that this was not the case. And so, rather than saying that the mass of just disappeared, which would be a violation of law of conservation of mass, or that the energy somehow managed to just disappear, which would be a violation of law of conservation of energy, there was a suggestion in the 1930s that there must have been another yet to be discovered particle, which was eventually called the neutrino. Basically, the neutrino has been discovered, and in beta negative decay, meaning electrons, an antineutrino is actually released. And we call that antineutrino, we use a little symbol like this. Okay, why is this not working? There, we are working. Antineutrino looks something like this. And during beta, and so this happens during what we call beta decay, negative beta decay, which is the electron. Now there's another type of beta decay, which is positive beta decay, which essentially is your positron. It's the antiparticle of the electron, and it is a particle. It has the same mass as an electron, but the complete opposite charge. And so we see the regular neutrino there. Now, the way that I keep this straight as to which one is which is the beta negative decay has the antineutrino, negative with the line here, with line here. Here, positive, no line, and we leave no line there, which is usually an indication of positive. I know it's not a great analogy, and some physics professors are probably cringing by hearing that, but honestly, it works. So when we take a look at some of these examples here, completing the reactions, here we've got francium becoming actinium. AT is actinium, yep. Or astenine, sorry. The charges need to balance. So 87 becoming 85 means that this needs to be a 2. And 211 becoming 207 and 4, because we got 211 mass on the before and a total of 211 mass afterwards. Charge of 87 before, charge of 87 afterwards. And so this winds up being the alpha particle, that helium nucleus. Because this is alpha decay, no neutrinos. Here, 99 and becomes 99 and 0. 42 becomes 43 and negative 1, so they balance to 42 and 42 afterwards. And so this is a beta negative decay. And because it's a beta negative decay, we also include the antineutrino. Taking a look at number 9, 17 and 17, 0, 9 becomes 8 and positive 1, so we've got 9 and 9. Beta decay and regular neutrino. Taking a look at number 10, 60 becomes 0 and, well, 60. 27 becomes negative 1 and, well, 28. And so that is going to be nickel. Because this is beta negative decay, we include the antineutrino. 52 becomes 52 and 0. 26 becomes 27 and negative 1. And so that is beta negative, therefore antineutrino. 149 becomes 4 and 145. 62 becomes 2 and 62. And therefore this is samarium. No neutrino here because it is alpha. Okay, that is it. If you've got any questions, let me know as you work through the homework. Other than that, have a great day.